In the last session, we discussed about why we require cache memory, its salient feature, and also about the hit ratio. Let me elaborate on the hit ratio for your better understanding. Hit ratio is nothing but what is the percentage of times or how many percentage of times the required word by the CPU is made available or is available in cache memory. When I say the hit ratio is 90%, it implies that 90% of the times the required word or data is available in cache. It does imply that remaining 10% of the times the requested data by the CPU is not available in cache. That is called as a miss. If the word is available in cache, it is called a hit. If it is not available, it is called a miss. And hit ratio is number of hits, total number of hits divided by total number of hits plus total number of misses. For example, if there are going to be 100 times the CPU is accessing cache memory, after those 100 times, 90 times the requested word is available in cache, which means it is a hit, and remaining 10%, it is not found in cache, it is a miss. The hit ratio is going to be 90 divided by 90 plus 10. That is 90 by 100, which is equivalent to 90%. When you keep the hit ratio high, it obviously reduces the average access time of your memory. And not only that, the CPU will access only the cache memory. It doesn't bother about the presence of main memory. It need not access the main memory at all. That means you are able to bring down the average memory access time from its actual time to the access time of your cache memory. Of course, you know, the access time of main memory is 1000 nanoseconds for illustrative purpose. Let us assume that way. And the access time of your cache memory is 100 nanoseconds. How will you calculate the average memory access time? If you consider hit ratio is 90%, 90% of the time it is found, the word is found in cache, which means 0.9 into 100 nanoseconds, which is equal to 90 nanoseconds. 10% of the time, the word is not found in cache. What CPU has done? First, it has initially accessed to cache memory. The word is not found. That means it has wasted 100 nanoseconds. And then it accessed main memory, and the word is found in main memory, and that is transferred from main memory to CPU. And the same word also gets transferred from main memory to cache, so that the future reference of that word will be found in cache. It will be a hit. So initially it has spent 100 nanoseconds, which is not fruitful. Then it fetches the requested word from the main memory, spending 1000 nanoseconds. The total time spent is 1000 plus 100, 1100 nanoseconds is spent whenever the word is not found in cache. It's called as a miss. What is the percentage of miss? It is 10%. Therefore, 0.1 into 1000 plus 110. 1000 plus 100 is equal to 1100. So 0.1 into 1100 results in, it is resulting in 110. And already we have found out 19.9 into 100 is 90, 110 by 90, 110 plus 90, it results in 200 nanoseconds. That means on an average, your access time is brought down to 200 nanoseconds. If cache is present, it is 200 nanoseconds on an average. If cache is absent, you are going to spend 1000 nanoseconds on an average. So there is a drastic reduction from 1000 nanoseconds to 200 nanoseconds for every word access, which means you are cutting short or you are reducing by 800 nanoseconds for every memory reference. So this drastically reduces the idle time of CPU and its performance factor gets increased. So how will you calculate the average memory access time? So 90%, that is 0.9 into access time of cache memory, or this, instead of saying access time, I can put this way, 0.9, that is 90% into speed of the cache memory plus 0.1 into the speed of access time, or the access time of your main memory plus access time of your cache memory. That is 1000 plus 100, 1100. This results in 200 nanoseconds on an average. So this is about cache memory. You can find the block diagram of a cache memory here as an example of cache memory. Main memory is 32,000 words, which means it requires 15 address bits. 2 power 15 is 32,000. And each and every word, each and every location for that matter has got a 12-bit data, which is called as the word length of the computer. In other words, this computer has got 12-bit word length, shortly referred as word. So the address bus is 15 bits long and data bus is 12 bits long. And cache memory size is 512. 512 locations are there in cache, which means we require 9 address bits to refer to each and every cache memory location, and each cache location stores 12 bits. And then if you look at the CPU can access both the main memory and the cache memory directly. If the word is found in cache, CPU forgets the presence of main memory. If the word is not found in cache, it gets that word or data from main memory to the CPU. So this is going to happen only when there is a miss. As long as it is going to be a hit, CPU will not refer main memory at all. So that is bringing down the access time of your average memory access time, or the access time of each and every word, thereby considerably reducing your execution time. This is the basic idea behind the concept of your cache memory, especially about the hit ratio and how to calculate the average memory access time. Of course, we did discuss in the previous session about how will you transfer data from main memory to cache memory. We normally call this as data transformation. There are 3 different techniques available. Since let me not go in elaborative way, the 3 methods are referred as associative mapping, direct mapping, and set associative mapping. Let us see in brief about the 3 different methodologies one by one. Let us go in for associative mapping. CPU address is 15 bits long because we consider a memory of 32,000 words, 32K, and each and every location has got 12 bits. And then this is stored in a register called argument register. So this you can recall content addressable memory. The content to be searched is placed in the argument register. And what are we going to do in cache memory? We have a cache location. Each cache location gives 12 data bits as output. And what are we going to store? We are going to store pair. What pair is going to be stored? Address and data are stored in each and every cache location. How many cache locations are there? There are 512 cache locations. That means out of 32,000 words roughly available in main memory, any 512 words out of these 32,000 words can be kept in cache. Each and every location can store one of the 32,000 words. And this is what is the basic principle behind your associative mapping. You know pretty well what is associative. It is also called as content addressable memory. We are going to access the content. What is argument register containing? The memory address. Therefore, we are going to simultaneously compare with all the location contents, which is using associative memory. For example, you are going to have the address as 01000. You can call this as your octal number. Why? Because instead of writing 15 bits in this binary, I can write equivalently in 5 octal digits. Why? Because each and every octal digit is equivalent to 3 binary digits. If there are 15 bits, 15 by 3, it is equivalent to 5 octal digits. Therefore, the 01000 represents octal address. And 0 to 777 also represents octal number. 2 to 3, 4, 5 also represents octal digits, not decimal digit, it is octal. What is equivalent of 2? 010. What is equivalent of 5? 1101. What is equivalent of 4? 100. Therefore, these 5 octal digits, when you expand into binary, that becomes each octal digit becomes gives rise to 3 binary digits. In total, 5 into 3 become 15 digits. So that's the basic idea. And what we do, let me explain the process behind this methodology. So CPU address 15 bits, which I want to get the content of the location, which is a 15-bit address. Therefore, what CPU does, it places in the argument register. And what your cache memory is going to contain, it is going to contain a pair, namely the address and the corresponding data. So assume it is going to be 01000, the octal equivalent of a 15-bit binary address. So what I'm going to do, compare simultaneously with all the addresses. Okay, 01000, is it found in cache? Yes. The corresponding data, which is 3450, again an octal number, is sent as the output to the CPU. From cache memory, it is sent to the CPU. This 4 octal digits is equivalent to 4 into 3, which is equal to 12 binary digits. So that's the basic idea behind this technique, namely associative mapping. What is the drawback of the associative mapping? You know pretty well. Associative memory is very expensive. Why? Because you have to store not only the content or the data, what is required, plus it requires match logic, and you have to perform comparison in parallel. Therefore, that results in your content addressable memory or your associative mapping technique very highly expensive. So to avoid that, we go in for the next technique, and that technique is called direct mapping. Before you go in for direct mapping, there are how many locations available? As per the example, your cache memory has got 512 locations. Your cache memory has got 512 locations. Out of 32,000 words, you can store only 512 at any point of time. If the cache memory is full, then we have to replace one of the words with the word required by the CPU. If the word is not found in cache, CPU will get that word from main memory. The same word has to be transferred to your cache memory as well. If the cache is already full, then we have to replace one of the words already present in cache. We normally call this as word replacement. What is the best technique available? You can think of the technique known as FIFO, first in, first out. So whichever word was brought in first from main memory to cache memory, that word will be replaced. In this example, let us consider this was brought in first into cache memory. This was brought into cache. This is your argumentation. This is your cache memory. How many locations are there? There will be 512 locations. 0 to 511. That is the decimal address. And each and every location will have the address of the main memory as well as the corresponding data. Which was brought in first? Your octal number 01000 was brought in first. Therefore, whenever a new word has to be stored, this address can be replaced with some other address, for example, 77777, and the corresponding data value, namely 300. Therefore, this was brought in first. This is replaced with the new address, all 5 sevens, and the corresponding data value gets replaced with 300. This is done by a technique known as FIFO, first in, first out. What is the next one brought in? 02777. If any new word is requested by the CPU, is not found in cache, then this was brought in next. Therefore, replace this by the new word with the corresponding memory address. So this is done by a technique known as FIFO, first in, first out algorithm. This is for replacement whenever the cache is full. If cache is not full, there is no need for replacement or displacement. Let us go in for the next technique, namely direct mapping. In direct mapping, what we do, we are going to have memory directly. We are going to make use of the memory. And what we do here, because your associative mapping is expensive, we want to cut down the cost factor. Thereby, we go in for the direct mapping technique. So let us consider the example here. Straight away, I can specify you. Your CPU address is 15 bits long, and we divide them into two parts: 6-bit tag number and 9-bit index number. How do you decide on the index? The number of bits in the index is based on the size of your cache memory. You know pretty well, your cache memory has got 512 locations. To identify 512 locations, you require 9 bits. Therefore, 9 bits are meant as an index. If your cache memory is, let me say, for example, consisting of only 256 locations, 256 is 2 power 8. In that case, your index will consist of only 8 bits. In this example, let us go by this example. Your 15-bit memory address is divided into two parts: 6-bit tag number and 9-bit index value. And then this 512 is the size of your cache memory. That means there are 512 cache locations, and each location outputs a 12-bit data value. So let us come to this part. The index is going to be 9 bits, which is equivalent to the 9-bit required to access your to identify each location of your cache memory. It is denoted in octal digit as 000, and then the last one is going to be 777. So 000 in octal is equivalent to 0 in decimal. 777 in octal is equivalent to 512 in decimal. 0 to 511. I'm sorry, it is 511. 0 to 511 is equivalent to 512 storage locations. Now what we do here, this is your main memory. Your main memory is 15 bits long, and data is going to be 12 bits long. And there are 32,000 locations available, each location storing 12 bits. This is your main memory configuration. What we have done here, we have divided your main memory address into two parts: a tag part and the index part. The index part is 9 bits. Of course, I did explain you. These 9 bits is based on the size of your cache memory. Since your cache has 512 storage locations, we require 9 bit to access each and every cache memory location. That's why we have the index as 9 bits. Now we have got 2-bit 6 bits of tag is equivalent to 2 octal digit 00, and the index is going to be 000. And what is the maximum value? 77777, because 7 is a maximum octal number, and the most significant 2 digits represent the tag, and the least significant 3 octal digits represent your index value. Now the index value remains the same. What are we going to do? We are going to store the tag and the corresponding data. Let us see in the next example what we do. So this is your main memory address 00000. This is your starting address of your main memory in octal representation, and the corresponding content is 1220. What are we going to do? We are going to divide this into two parts. The most significant 2-digit 00 is your tag, and the least significant 3-digit 30 is your index. So this index represent your cache memory address 000. What is the tag value? 00. Therefore, we are going to store the tag and the corresponding data value. What is the data value? 1220 in octal, which is equivalent to 12 bits in binary. How do you represent 1220 in binary? 001, 010, 010, 000. This is equivalent in binary consisting of 12 bits. Then let us go in for one more example, namely 00777. So when you go in for 00777, 00777, so when you go in for 777, we have to store already 02 is stored. So what is the tag here? 000. What is the corresponding data here? 2340. Therefore, we have to replace the 02 by the tag value 00, and then the corresponding data value is 2340 should be overwriting 6710. So this is how you do in the case of your direct mapping. So what we do, the 15-bit address is divided into two parts, the tag part and the index part. Tag part is 6 bits and the index part is 9 bits. The tag part represent your most significant 2 octal digits, and the index part represent the cache memory address. To identify a location of cache memory, we require 9 bits, which is represented in 3 octal digits. So therefore, the index represents the address of your cache memory. And what we do, we are going to store the tag part and the data part as a part of your cache memory. So whenever you are giving the memory address as 00000, that is, it is stored in your argument register. Let us go in for here. If it is stored in the argument, if it is going to be stored, then it comes to the memory address 000. It looks for the tag 00 here, and correspondingly you get the data value 1220. This reduces the cost factor. That is the advantage of direct mapping technique over your associative mapping technique. It reduces the cost factor, it reduces complexity, and there is no match logic required. So that is the advantage of direct mapping over your other things. Now, let us go in for one more example. So what is not possible? We cannot store in the index 000 more than one tag. See, index can be 000, tag is going to be 00. Similarly, you can have the tag as 01, index can be 000. There can be only one tag and the corresponding data present inside the index address 000. So 00000, this is one. If I am going to have 00001, 0 or 01000, 01 is the tag and the index is going to be 000. The index is common, but the tags are different. In the first case, the tag is 00. In the second case, the tag is 01. You cannot store both under the same memory location 000. We can store only one tag as a part of the index value. We cannot store more than one tag as a part of the index value. This is a drawback of your, let me say, your direct mapping technique. Instead of only one, probably we can go in for, we normally call them as a block. That is an advancement of this direct mapping technique. You need not bother for the time being. So the point you have to keep in mind, what we do, we store in each and every cache memory location, we store the tag value, which is the most significant 6 digits or 2 equivalent octal digits, and the corresponding data value. At any point of time, out of 32,000 words, 512 words can be present in cache memory. 000 represents, as I mentioned before, it denotes decimal number 0, and 777 represents decimal number 511. So 0 to 511, it is equal to 512 storage locations. This is direct mapping technique. The disadvantage, for a given index, we cannot store more than one tag value. So that's the drawback of direct mapping. To overcome that, you go in for the next technique, namely set associative mapping. So we will see an example of set associative mapping. This is called as two-way set associative mapping technique. What do we do here? We have got the index 000, we have got the tag 01, and the data value is 3450. Now, the index remains as 000, but the tag is what? 02, and the corresponding data value is 5670. Data value is 5670. So see, we are storing under this index. We are storing under the index, that is in one cache location. We are using the set associative mapping technique. Thereby, we store two different tags. This is the tag and the corresponding data, tag and the corresponding data. This is two-way set associative mapping cache methodology. It could be, even it can be 4 ways. What is meant by 4 ways? 4-way means 000 is the index. You can have the tag as 01. You can have the tag as 02, you can have the tag value as 03, you can have the tag value as 04. Under one index, you are able to store 4 different index values and the corresponding data value. Therefore, you perform comparison in parallel, and when you go in for the index value 0, 0, 0, simultaneously all of them are compared. Whether the tag value 0, 1 matches or 0, 2 matches or 0, 3 or 0, 4. Whichever is going to match, the corresponding data, which is 4 octet-digit number, will be sent as output. So this is the basic idea behind your catch, two-way set associative mapping technique. So let us go in for the next one. Replacement algorithms. I already did mention about what is a replacement. One is least recently used. Other one is FIFO, first in, first out. So these two algorithms you will be learning when you are coming across a subject known as operating systems. When do we do this? Whenever the cache is full. Of course, you know there are only 512 storage locations in cache. When cache is already full, you want to transfer one word from main memory to cache memory. If it is already full, we have to replace one of the words found in cache or present in cache. That should be removed, and we have to store the new data from main memory into the cache. And that is where we make use of a technique called replacement technique. And there are a number of techniques available. The two popular ones are FIFO, first in, first out, and the second one is LRU. So FIFO, it works on the first in, first out strategy. And LRU stands for least recently used. Yes, let us not worry about how LRU works. For the time being, you can stop with FIFO is one of the important page replacement algorithms, which is working on the principle of first in, first out. Then how will you write data into cache? There are two methods available. One is write through method, another one is called write back methods. So what do we do here? Let me go in for the take up this diagram, which will be better for you to understand. Yes. So whenever CPU is going to update data in cache memory, in the case of write through method, you are going to update the data in cache memory as well as in main memory. That means parallelly you are going to update the same data or the same word present in cache memory as well as the same word present in what main memory. So this may consume time. This is called as your write through method. In the case of write back method, what do we do? In the case of write back method, we'll be updating only the cache memory. We will not be updating the word that is present in main memory. When do we update? When the word present in cache memory is no longer useful, or when the word becomes inactive, then you are going to copy the word from cache memory to main memory. At that point of time, we will be updating the word present in main memory. Not every time the cache word is getting updated. Whenever a word is modified by the CPU, if you update in both in cache memory as well as in main memory, that technique is called as write through method. If you are going to update only in cache memory alone, as long as the word is active, once the word becomes inactive, then you will be transferring the word from cache memory to main memory. At that point of time, the main memory will get the latest update. Till such time, it will be having only the old value and not the latest update value. So this is called as your write back method. So there are two techniques, write through and write back. Write through updates in both main as well as cache, and write back, it updates only in cache. So this is a point you have to keep in mind. Then before you perform any operation, the cache memory has to be initialized. It can be done, that is making it empty. How it can be done? We can have one more bit associated. Maybe I can go in for your cache memory. With each location in cache. Yes, with each location in cache, I can have one more word, one more bit associated. That is called as your valid or invalid bit. Whether the word present in cache is valid or invalid. Valid means it is active. Invalid means it is not referred by the CPU at all. That means it becomes invalid. So you can check whether the word is valid or invalid. If the tag is going to be 1, the word is valid. That means it should not be disturbed. You look at your tag register, you look at your valid bit register, whether it is valid or what invalid. When you come across the first 0 bit, that means the word is invalid. That can be replaced by the incoming word. So what do we do when you go for initialization? We keep the valid invalid bit as 0. Initially, when cache is initialized, the valid invalid bit is reset. Reset means no word that is present in cache is valid. That means even though some data may be present in cache memory, they are no longer required because it is reset. Whenever you transfer a word from main memory to cache memory, what do? We not only transfer the word, and we replace or we change the status of your valid invalid bit from 0 to 1. So whenever the valid bit is valid or whenever the valid or invalid bit is 1, which means the word is active or it is valid. When I can call it as active or what valid. Whenever the corresponding bit is 0, the word is invalid or it is inactive. So this is what you should keep in mind, because cache memory has to be initialized. The last but not the least, when you have two different methods, namely write through method and the write back method. The important difference in write through method, you are going to update your cache memory as well as main memory. In write back method, you'll be updating only the cache memory and not your main memory. So this is about cache. And there are three different techniques available. Keep in mind, the first one is associative mapping. The second one is direct mapping. And the third one is set associative mapping. You know the pros and cons of each and every technique. Kindly keep them in mind. The important points you have to remember are the purpose behind the cache memory, the principle of cache memory, hit ratio, property of locality of reference, how data transformation is taking place. We normally call them as a mapping technique. And then how do you write data into cache and how it gets initialized. And of course, how do you perform replacement, whether we're using FIFO technique or LRU technique. And last but not the least, with each and every word, with each and every location of your cache memory, we attach one more extra bit that is called as the valid or invalid bit. Whenever it is 1, the word is the corresponding location contains a valid word. Whenever the bit is 0, the corresponding cache location contains an invalid word. This is what is about cache memory. Remember, cache is quite expensive and its speed is roughly 10 times faster than your main memory, and roughly they are in the ratio 1:10. And of course, you do remember cache memory, the speed is its characteristic feature and it is based on the principle of static RAM. And its memory capacity is in terms of megabytes. So that's about cache memory. And in the next session, we'll have a brief intro about virtual memory.